Okay, so today we're going to talk about hopefully fixing a common complaint, at least I think it's a common complaint, or at least my complaint with Tiano EDK2-based solutions, which hopefully will revolve around embracing modularity and fixing some of the firmware configuration issues seen. All right, so I'll talk about the background and the solution. Easy. Okay, so UFI, as in the spec, defines a rich and flexible driver model. And of course, also some bus manual interfaces. And you can see these inside the Tiano core code base. You've got SCSI bus, PCI bus, right? The whole mechanism exists so that in your typical use case of booting an operating system, you're standing up only the device drivers that you need for the boot. Okay, so that works well for discoverable devices, PCI bus, but what about platform devices, or the SoC devices? So a lot of the stuff, as it's done in practice, because these are non-discoverable devices, end up being very fiddly and kind of done, in an ad hoc manner. When you look outside of Tiano, things look better, or at least for at least one implementation. Okay, so this is a pretty important subject because this is friction to porting Tiano to a new platform. If basically you have to kind of look inside yourself and figure out, like, what is the correct mechanism? How do I, if I want to support this network device, which is a compound device with 3 separate things, or if I want to support this onboard video, which is a combination of 6 separate blocks, what is the right architecture for that? Like, what is the right layering? Is that a single monolithic driver or whatever else? If you have to do that and you don't have to do that with like other UFI implementations, you might be tempted to go adopt those other implementations. All right. Now, Tiano is a reference UFI implementation, and for many, so Tiano is UFI, but UFI is not Tiano because you can have multiple different implementations. But things that are gaps in the reference implementations are frequently claimed as UFI gaps by people who want to find issues in UFI. So fixing such problems isn't a bad idea. Okay, so one problem is I want to support minor SoC variations, okay, or I want to support different board designs around the same SoC, and in practice, my platform devices hardcode register the CSRs, the registers you use, or whatever else, as pound defines or as PCDs, whatever else. So I have multiple, DSC and FDF files. So it's all kind of compile time-based, call it dispatch maybe, but that's not the right word. Some platforms adopt kind of their own custom ways of having a generic view to the platform. The Marvell Armada 7000, 8000 code, it's an EDK2 platform, so here's a link. It has a library that driver code can say, hey, how many of these blocks do I have? Or how many of these blocks do I have? Okay, which again, kudos to that vendor for doing that. Although it's unclear if it's like fully runtime, it is still compile time. So it's not as if you can use the same binary on a 7000 and 8000 SoC. Okay, another problem is that many of these platform device drivers are not necessarily implementing the driver model. So some of these just install like whatever protocol you want. A good example of that is the RNG driver in the Raspberry Pi. I think that's the Raspberry Pi 3 RNG. But device, driver entry point, boom, install protocol. All right. So that's one. Again, that's a pretty simple example. It's just the cost of installing a protocol. But you can have drivers that actually initialize hardware, so now you're taking the latency of initializing the hardware. If you're always installing the protocol, then there are other kind of onion layers that can appear. If you go back to the promise of what UFI was supposed to do, is that in the generic case of the common case, sorry, of booting and install OS, you're supposed to initialize at minimal surface, not just starting everything up. Okay. Okay, so other examples are, well, some drivers are generic drivers, but they have like a custom specific library that they kind of eat up. A good example here is serial port lib, which is eaten by serial Dixie, and then serial port lib actually implements what does it mean to talk to serial port. Another one is the generic PCI host bridge, PCI host bridge Dixie, which provides the config space abstractions to the system. That one takes this host bridge with. Okay, so it's a fairly limited example. It's an example. Others are drivers that will publish a driver binding protocol, and then will pop up the one handle that they will install on. So this gives you some benefit of you can actually disconnect and connect the driver again. But again, let's say I have a USB controller driver like that, and it's hard coded to start at specific register, MMIO registers. If I'm going to go into another SoC with the registers with 2 more of these blocks, I still can manipulate the driver, right? So again, not particularly great. Another problem is, well, you end up with monolithic drivers. A good example is a NIC, which is a combination of like the NIC engine and the DMA engine and the actual PHY. Well, and you're talking to multiple memory mapped IO devices. Your PHY might be sitting on an I2C bus as well. So again, depending on the complexity of your firmware, maybe you're just hard coding the I2C transport in your driver too. Everything's just going to jam together, right? There's no like PHY framework in Tiano. Okay, next aside, the video frame buffer is another example. I want to render the video console for your PHY, and let's say you got maybe an ISP signal processor with multiple video inputs, which could do pixel conversion. You might have the actual kind of LCD controller that has a frame, handles a frame buffer memory. You might have an HDMI encoder, which you also need to configure. It sits on some I2C bus. An EDID source, so you know what refresh to actually configure. GPIOs, power rails, the whole shebang, right? Now you can do this once, and you can create this monstrosity, but then if you also want to support, let's say, on a laptop, output using the HDMI, you got to figure out how to jam that in too, and then add detection and all this. So do monolithic drivers, first of all, they're hard to write. Now there's no code reuse, and they're hard to tweak because it's all over the place. There's no, I mean, you can be smart and come up with your own structuring and layering, but a lot of work. So again, minor SoC variants end up using different dedicated builds, right, with PCDs or custom drivers or whatnot, and have a situation where same SoC, even minor platform variations will end up saying, here's a build with this PHY driver, there's a build with that PHY driver, or other custom bits, like on this board I have 2 root complexes, on that board I have 1 root complex, things like that. So, okay, all right. So do we have a solution? Yes, we don't have to necessarily invent this, it's already been done. U-Boot, as a firmware implementation, also has a rich driver model, and has the ability that if it takes a device tree blob, either from a previous booting stage or was embedded, it will use that to stand up and configure the drivers in itself, okay? Which is a pretty powerful model. Okay, aside, what is a device tree? At the most basic level is a binary data structure, which is a marshalling format for hierarchical key value. It's a key value store. That's really all that is, but there's a spec. Here's the link. It came from the PowerPC world. It was embraced by ARM and recently the RISC-V platforms. As a generic marshalling format, it has been used in the vertically integrated, quote-unquote, embedded space to describe the hardware to an OS. Don already talked about limitations of that kind of an approach. Again, it's used in place of ACPI in these sort of more embedded-like environments. Is this talk about ACPI versus device tree? No, it's not. Because ACPI versus DT is what do you pass the operating system. Like, this is not what this talk is about at all. Now that choice is done elsewhere, let's put it that way. Now, like I mentioned, DT is a very generic container for passing information. Many reasons why some might object to device tree being used by operating systems are, well, lack of a common industry-defined schema, compatibility, all that, lack of abstraction. All of these are, they don't matter. They're actually, you could look at them as benefits because it's just a structure to convey information, from your own platform that you control to your own firmware, okay? So like if you look at the API spec, there's that HOB, the handoff blocks. This is kind of like that on steroids, right? It's just a description, and it's a hierarchical description of devices, and it allows for a pretty interesting and complex descriptions. Hopefully that's large enough to see, but this is an example of an Ethernet device from a Raspberry Pi 4. What you see here, like there's a top level Ethernet device. You can see like some interrupt it's using, where the registers are. You can also see that there's a child device to describe the interface to the PHY, and that itself has another child device which describes the actual PHY and where that lives at. And again, the properties that are here, like yes, this is consumed by Linux, but in practice, things you describe in the device tree are what you'd expect your device drivers to need and to use, right? So if you're interested in, say, consuming this in a UEFI driver, right? You wouldn't need, you wouldn't care about interrupts because the UEFI is not really interrupt driven outside the timer tick. But as a description, this already gives you the kind of this layering of like, okay, so I have an Ethernet device, I might have a PHY device. The PHY device might be handled by a separate driver. All right. Okay, device tree, but is this something that's actually existing in Tiano core today? Yes. So on ARch64 ARM, the 32-bit ARM, and the RISC-V, UEFI is frequently, it gets the device tree from higher, more privileged firmware. On ARM, it gets this from TFA. On RISC-V, it gets this from OpenSBI. How is it used? One way, most basically, it's not used at all. It's certainly not used by drivers per se. When it's passed to the OS, so when it sticks to that eBPR system ready IR profile that Dom talked about, when it's used for OS description, right? It's patched up, and by UEFI, and then passed to the OS. It certainly can be traversed in drivers. There's a library called FDT client that is that's meant for that, but it's basically like you know what you want, and your driver goes and gets it. A good example of this is OVMF platform, virtual UEFI for QEMU on RISC-V will use FDT client Dixie to configure the VirtIO device driver, right? So you can get block storage and things like that. Okay, so it exists. Another few points is again for platforms that I guess I'm talking about, DT blobs already exist. Whether you want them or don't want them, Linux is frequently used to bring up new hardware. That's done. Device tree allows for quickly prototyping, say, Linux support without getting all the other firmware bits in place. ARM and RISC-V, and so almost all platforms already have DT. And then as part of enabling, they may add a CPI support depending on the use case. But again, DT is not actually architecture specific. So could you use this in x86? Yes. Long arch, whatever else. Okay. So wouldn't it be great if we actually use the hierarchy afforded by device tree, which is already used in operating systems to detect if a driver needs to be loaded and then to bind that driver to the device? Wouldn't it be great to do this in UEFI? I mean, hopefully the answer is yes. Okay, so NTT Buzz Dixie, it's a UEFI bus driver, like PCI bus or anything else. Obviously the work has started at Intel, I'm at Intel, but we are actually open sourcing it. So it is going to be open sourced under the obvious BSD license. Now this work is actually going to be done under the auspices of the RISE project. RISE is a RISC-V software enablement. So it's like Linaro, for those of you familiar with that, but for RISC-V. So it's a non-for-profit umbrella org where a bunch of companies collaborate to work on commercial readiness of open source software. So it's divided into multiple multiple working groups. One of these is the firmware working group, and this project naturally falls within that. And there is some interest, within that working group. Some members are going to say, yes, we are already doing something like this because it's common sense. Let's do it together. Okay, so it's getting really close to where you'll see some code really soon. Okay, so that's a promise I'll meet. Okay, so the driver obviously binds. It binds to the device tree blob. There's a hierarchy. There's a root node there. It binds to that. It also device tree contains nodes and how they're structured, where they can be all flat under the root, but they're actually grouped up, and you can have sort of these basic container-like nodes. They're kind of like ACPI 004 containers, if you're aware of that. Okay, so that's all great. And then for the nodes that are enumerated by the bus driver, you get the requisite I/O protocol abstraction. Just like PCI bus, you get you the PCI I/O protocol. What does this do? Well, it gives a driver the ability to fetch some obvious info like name, model, status. You can look up arbitrary properties, to get whatever custom configuration data you may need to program the device on this platform. Of course, because device tree nodes usually describe physical devices that have registers, having an interface to abstract register accesses makes sense. So there's that. And then because more complex devices they're DMA driven, and because device tree also describes the DMA constraints, basically where there is no one-to-one mapping between a bus address and a CPU address, or constraints on min-max. Again, an API to manipulate DMA buffers. So there's that. Okay. FTT bus Dixie can be a drop-in replacement for FTT client Dixie, in the sense that if you're exposing DT, to the OS, you can do that. But we don't bother implementing that FTT client protocol, right, that I talked about, thing in the black box. We don't do that today, I guess. All right, so what else? Okay, so you look at this example, and let's look at properties, right? So actual properties, right? What is a property? A property can be, going back to this example, you can have strings, integers. You can have like an array of values. A property can actually reference another device node, or you can have completely mixed things, right? So you can have like, my custom property might have a string, a value, and some other things in a reference, right? Okay, so when you think about it, like how could you abstract property lookup? Okay, so the kind of the API that's created here, it treats the property value as a stream of data, so you can sequentially kind of read things out of it, okay? If you're going to get a property, get a structure that basically says, here's the beginning of the byte stream, and here's the end of it, and here's the current pointer to it, and then you have another call that lets you parse things out of it. What kind of things? I want to parse a 32-bit value, a 64-bit value, a bus address, which, by the way, is kind of funky because, again, there are other properties that describe how wide the bus address is, or the size of a bus address, again, kind of funky because that's controlled by other properties. It could be a register, which again contains a bus address and size. It could be a range property, which is used to encode the DMA limits. It could be a string, and it could be even another device. Okay. So again, this parsing can be kind of complicated. So when you look at a property that encodes the CSRs, or the device registers, how wide is the bus address? Well, that depends on the parent address size. Right? How wide? What about the size? That depends on the size. So in this example here, you see that address cells and size cells as well. A cell is 32 bits. Okay. So here you see that I have a reg, and there's exactly one cell that says it's 4600, and then there's another thing that says the size is 100. Okay. Another thing is that, well, just because you read the reg property, that value itself is not particularly useful to you. You probably want the CPU address, and in order to get that, you need to go up through the parent nodes and see if you can translate that all the way to the root and see that's a CPU address. So in this example, you'll see that this 4600 value, like is that you look at the parent range property here. What that says is that the child bus address at 0 is mapped to the parent address of E000. Okay, so you can see if does the child reg fall within the range? If so, yes. Then you can obviously add things and get it. You get all the way up, to the root node. It's a CPU address, and you can actually do accesses. But if you don't, then you kind of hope that the device driver for the parent node must have I/O accessors, right? Because maybe it has a crazy way of doing an I/O, right? An example of that is a certain ARM server vendor did a non-standard implementation where they had a UART. and the UART had registers, but those registers weren't confined to sort of CPU addresses. You actually had to go talk to an LPC chip and do that. So again, device tree is descriptive, and then the API allows you to kind of translate these things. Okay, so the I/O access API allows you to, it's again modeled after other bus abstractions. So you can read a register, write a register, pull a register, wait for it to be a certain value. Obviously, this API must be hookable by the driver, because again, what if child register reads are not CPU register reads, so that be serviced by some other driver. Right? So you must be able to hook that. Another thing is DMA buffer accesses. Again, buffer handling can be complicated because first of all, given a child device, the parent for that will say, okay, child knows about these bus addresses, but here's how they map to my bus addresses for the parent. And then you can translate this all the way up and ultimately end up with a view of, here are the bus addresses for my device, here's what they actually mean to memory in the system. Now, you can have restricted I/O capabilities. So a good example of that is devices on the Raspberry Pi 4, the bus address starts at 3 gigs, right? But the actual system address is at 0. But you can only access 1 gig, right? So if you want to allocate a buffer to DMA into for the USB 2 controller, you better allocate it within the first gig. Okay. Also, the device DMA may not be cache coherent, and again, this is a common issue when you look outside of the server space and the SoC, SBCs, the Raspberry Pi like hardware on ARM and RISC-V. Again, that has implications on how you allocate the buffer, or how you map the buffer, what kind of maintenance you do on the map and map operations. So it makes sense to make this part of the FDT bus API. So if you write code, you don't have to worry about barriers or having to know about doing cache flushes and such. So hiding this, the bus driver really does know best, because again, it has the full picture because it sees a full device tree hierarchy, and of course it runs on a specific architecture, so it knows some of the limitations there. All right, so great, we have this bus driver. So how do you actually, what does it mean to use it? So there's 2 usage patterns. The one that I would really like to talk about is the driver binding one, which is the one kind of prompting this whole thing being developed. But of course there is, I would call it a legacy model, whereas you write just a driver that is not using the driver binding protocol, and like this FDT client Dixie, you just manually scrape the tree looking for things that you want. Again, there are some drivers which are somewhat tedious to, it's possible to rewrite them, but they're kind of hard because it's a driver that links to a library, right? Again, the PCI host bridge is one of these, and the sort of portal. So these drivers are already not driver binding, and they expect all the platinum dependencies to be hidden inside this static library. So again, yes, you could write the static library to just look up. Basically, you go look. Let's see how it's done. So the example I want to show you is OVMF, so QMU virtual UEFI. There's a driver for supporting head memory, where basically it will support a booting, just add the memory ranges above 4 gigs. So this was an example driver, one of the drivers we rewrote to use the new driver. So the legacy way could be like, okay, so this driver depends on the presence of the new protocol, which sort of means it depends on the FDT bus driver loading, okay, so it won't start before that. And then in the entry point for that, you're gonna find all the handles with the DTIO protocol, iterate over them, right, and then see if the node looks like the one you want to support, you're gonna go and process it with some function, okay? Which is exactly how this code looks like if it uses FTT client Dixie. The driver binding mechanism looks different, of course. The entry just installs the driver binding protocol, nothing else. Now the driver binding protocol, if you recall, consists of 3 methods: supported, start, and stop. And the supported method is called on basically every handle is published. So driver supported gets called, it first of all sees, hey, is the DTIO protocol present? Yes, okay, good. So maybe it's one of mine. Then you go and see, well, is the device type matching the kind of object I want to support? Yes, okay. How about device status? Is it present memory? Yes, okay. So you report okay, success, and then of course the driver start, and it does the deed and end processing memory ranges. Just for completeness sake, when you talk about processing memory ranges, here's what that roughly would look like. Again, what you see here is that you see get reg being called, which is a wrapper just around get prop and parse prop, and you see that this will basically keep parsing register ranges out of, because again, reg can like multiple ranges. So for every range within the reg property, it will go and get this, and then of course call some function to process that memory range. All right, nothing particularly crazy. Okay, so maybe you're thinking like, oh well, what you by converting this to driver binding, you've actually introduced a problem because if you're doing a full enumeration boot, like if you don't know what you're booting, you don't know what OS you're booting, the BDS goes into full enumeration. So I'll try to connect every single device to everything, and sure, this will fire. But if I'm actually booting an OS, then how will I ever even connect this driver? Right? It's not in the boot path. Okay. So this is where we create a problem, we create a solution. Certain nodes are critical nodes. Okay, you can either mark up these nodes using properties, like say, hey, it's a critical device, must have this connected, or some nodes like memory, right, are just critical by themselves and just have to exist. By the way, this is not necessarily a problem that only exists this way. There's one DPU vendor that did a stellar job in the UEFI implementation, but maybe too stellar because the PCI root complex, again, would only enumerate if it was in the boot path. And technically, if you read the PCI firmware spec, it actually says that, if the OS is not booted from PCI Express, you don't have to configure it. In practice, a lot of OSs actually expect the root complex to be configured. So if it's not configured, things go kind of south. So, okay, more examples. Hey, this is actually pretty legible. Okay. So on the left, you see this is the device tree command on the UEFI shell on this OVMF QEMU. So this is kind of nice. I mean, it's different from your typical device tree in such a platform where you can actually see the hierarchy of here's the root node there, and then there's a bunch of nodes, and I see there's an SoC node, and underneath that I see some VirtIO, MMIO nodes, which are VirtIO devices. And it's obvious that one of these is a block VirtIO device because it has a file system driver attached to it. So this kind of gives you a nice at a glance view of okay, devices, drivers are connected. So obviously, if all your devices in your platform are discoverable because they're PCI devices, you already see this. But a lot of them, all modern SoCs don't do that, and they have platform devices. So. Okay, all right, so the thing on the right is how you see, you might be wondering, well, you're writing a lot of code here. How do I know any of this stuff is correct? So there is sort of unit testing built into the driver. It only runs on debug builds. But effectively, there is another built-in, another device tree that we just create on the fly just for the purpose of testing the API. And so that's what you see on the right. There's another thing with just those, they're just there for the driver itself. So, kind of ran through that in 30 minutes. This was originally a 45-minute talk, but I know we started a bit late, so maybe that's okay. Does anybody have any questions? Happy to answer.
How was it evaluating the performance of the device tree and storing nodes and system such as traditional system was kind of package?
Well.
Try and repeat the question back because.
Okay, so the question was, what's the performance like of actually, parsing device tree and all that? Okay, so I don't have direct numbers for you. Okay, so maybe that already answers your question, but I have some good news. So first of all, so device tree is kind of you could say is to a degree kind of a signal path data structure. So at the let's look at this device tree example, right? So the bus driver will bind to the root node. Okay, good. It will then enumerate the handles right below that, which are everything you see here up to SoC. Okay. The SoC one, it discovers its support because it's a simple bus one, and then it also enumerates the chub handles under that. and that's it. Does not enumerate, you know, it cannot enumerate anything deeper, right? Because that needs to be done by the actual driver, right? So one of the APIs I maybe didn't mention is if you're writing a driver that basically your device tree node has children, then there is an API to go process those and register those nodes as actual handles as well. So the reason why you're doing this though, right, is because you want to avoid the cost of drivers that just initialize because you don't know better. Which again, if they're not, you know, if they're following a sort of monolithic model, or saying, hey, I'm just going to install a block I/O protocol or this other protocol, right? If you're not in the boot path, right, and if you're not doing a full enumeration, you're still taking that cost of like, well, I don't know why, but I'm always going to initialize the SD controller, regardless of whether it's in the boot path or not, right? Like that provides extra latency, right? Scanning the PCI devices would add extra latency and so on. So this is going to save you time, right? Now, parsing DT itself is pretty simple. Right. Again, from a totally unscientific test, so running this in QEMU, I don't see it, and it's not like the cost of saying, well, let's add an AML interpreter, right, and sit there again and wait. No, it's extremely thin because again, DT is just a simple binary Marshall format. Yeah. Now, again, I'm not right. I mean, I've been involved tangentially in UEFI development for like 17 years somehow, but I have never worked in IMV. Now, from hearsay, I know that IMVs and SIPs roll their own description mechanisms for just stuff like this. So, is there a cost to those? Of course there's a cost to those, right? But there's a value to those too, right? Now, what I'm saying is you could go check that. Well, why would you want to do that? Because for many of these platforms, you already have device tree, and because device tree is probably more descriptive than the mechanisms you have, but I've not seen the mechanisms.
Out of interest, if you have a socket with, say, 100 cores, how many nodes would you expect in such a device tree?
If I have an SoC with 100 cores,
Yeah.
well, the CPU cores are the CPU nodes, right? Which would be, if you look under this thing, they would be nested under.
I mean, you also have associated additional things around it.
Well,
get
again, sure, but like your 100 cores would sit directly under this DT CPUs. Like in this platform, there are 2 cores or hubs. There's a RISC-V system, but I don't have a CPU driver. It's not able to ever bind to that. What other associated things? Again, they might be there. They might be nested under an interrupt controller handle. It sort of depends, right? But the short answer to your question is find out. Try it out and find out, right? I think one of the so again, I talked about working in open sourcing this, right? Again, before doing that, I want to have a reference implementation that exercises the API. Because again, that's already a pretty good proof point that the API is solid. So we're doing that with the QEMU VMF example, but it'd be really good to have a real board. Again, it does this as well. I think the Raspberry Pi UEFI implementation is a good example of that because it's a common pattern there for a driver that just installs a protocol. So I don't anticipate the cost to be significant. With this, I mean, effectively, what you are doing here is you're trading space for time, and time is where things are, where you actually want to be. I'll give you an example. When I first made the 64-bit Raspberry Pi UEFI port, it booted faster than the equivalent U-boot port, like to the OS. It could boot video, SD, USB, boot OpenSUSE, and it did that faster than U-boot, right? And I really, when in 2006 I got sold on the premise. My employer at the time told me to love it. When I read the book, and I loved it because it said, we're going to shorten the boot times, right, to make them insignificant. Now, you have to see a server that boots faster than like 2 minutes. But hey, at least on the PCs, UEFI does actually go pretty fast. So effectively, yeah, you're saying you're adding more structuring, and more memory use, at least in terms of handles and protocols installed. But the premise is you will only initialize, first of all, the hardware that you need to initialize. But the real benefit I see here is you could stick to a single binary FD image that you distribute for all of your platforms. Like, here's your SoC, and it's in this platform, and that platform, and this one. Single image, not to make 10 different things, right? Or if you have minor variations in your SoC, again, you could handle this with the same minor image. You don't have to rebuild UEFI 10 times. So I see that as a benefit now, but again, I'm not an IV and OEM, maybe you don't. Don't.
The reason I started the question is because it seems like you're still developing and testing it where the number of nodes that you are experiencing is quite limited, whether it's because it's integration or whereas when you look at something like a number of interrupts that you have in a large SOC, like that's thousands, and if you have any kind of recursive check because the nodes can refer to other nodes, then like the data set can be pathological and
Well, so remember how the bus driver the bus driver itself only binds to very few items. It binds to the top level root handle, and it binds to the container nodes. Everything else, like you say, thousands of nodes or weird hierarchies, the implication is you have drivers that are enumerating those devices. So the cost that you're alluding to only exists if your UEFI implementation is going to actively bind to every single one of those UEFI devices, which is just not true. And then you could say, well, what about your operating system? What's the cost of your operating system scanning your device through thousands of nodes? It's the same thing. So it already exists. And you could say, well, and going back to the other John's question is, what's the cost of scanning a device tree in Linux? I don't think anybody bothered to measure it because it's not significant. The difference, though, by the way, in UEFI doing this in Linux is Linux, by definition, has to start up every device that has a driver for. With UEFI, unless you're doing full integration, you don't. You only start out the critical devices, right? The ones that have to exist no matter what you boot. And you have to start up the ones that are described by the device path components, which, again, are not going to be thousands. And the code is written in a way where it is going to go and specifically start up specific items, not generate you reams of kind of additional data structures and drivers being loaded accidentally as part of you looking at the